Now that you know the basics of what a FIFO buffer or a first in first out buffer, let's go and build some. Well, we can technically write HDL code to describe it, but it's outside the scope of this particular course. However, because FIFO buffer are super important and super useful, and I've seen them in multiple and many implementation, I just want to show you a quick way to incorporate it in your design without writing a lot of HDL code. And the way we're going to do it is we're going to use some of the available IPs that come with Vivado or from Xilinx. So if you actually go to the IP catalog in here, you have that search box. All you have to do is just write FIFO, and it'll throw the book at you. I mean, there's so many of these FIFOs in here. Some of them are AXI, like the AXI bus, or the XI bus. We're not going to deal with any of these. We're going to just go to the memory and storage elements. Inside it, there's FIFOs, and there's something called the FIFO Generator. And it's actually a wizard similar to the clocking wizard you might have used. Okay, so you double click on that, and you get this customized IP. Of course, if you want to know more information about all sorts of FIFOs, you can click on the documentation and read it. I'll just walk you through it. Technically, this is what I usually look up, this table. So I can see that the way we can actually generate several different FIFO implementations. So we have these in here, and it tells you the memory type it's utilizing, and you can actually choose them from here. So this table here tells you which FIFO you want to implement. It's one of those, and it describes it very briefly. So for example, this first one here, which is highlighted, is the one because that's the one that is selected. It will use block RAM or BRAM on the FPGA, and it's telling me that 1 and 2 are checked. So 1, well, you can use it for non-symmetric aspect ratio. What does that mean? Well, you can push data that is, for example, 8-bit, and you can read it as 4-bit at a time. So this is why it's called non-symmetric or asymmetric aspect ratio. Okay, and then 2, it tells me that this is of the type first word fall through. So if you write something to an empty buffer, it will just directly be available at the output. You don't have to wait for the next clock cycle. Okay, and then 3 uses built-in FIFO primitive. In this particular Arctic 7, I don't think there is a FIFO primitive. I might be mistaken in that. And 4, it's actually something to do with error correction and dynamic error injection. We're not going to talk too much about these. Of course, there's other implementation. For example, instead of BRAM, let's assume that you want something with a distributed RAM. It highlights it and it tells you, well, you're going to be using distributed RAM and so forth. Now, the most interesting thing, 2 things that I usually use are the one using BRAM. So this first one here uses BRAM, and there's another one here called independent clocks. So this one here is called common clock for a reason, because as you might recall, a FIFO buffer like the one here is used to connect the system on one side to the system on another side, and these 2 systems might completely be running at completely different clock speeds. So you can technically run a FIFO using one single common clock. So you can think about it as like, well, the first system is going to provide it with 100 megahertz, and the second one will provide it with 100 megahertz. But it doesn't have to be this way. You can actually use independent clock, one for read and one for write. So meaning the first system might be providing it with 100 megahertz clock, and the second system will be providing it with maybe 200 megahertz clock. So if you actually take a look at these independent clock, you can see it will add another clock in here, a write clock and a read clock. Okay, and you can see the synchronization stages, like if you have some sort of a synchronization between the clocks. Anyway, I think for the purpose of this course, the first common clock is actually enough. We're going to be using the native, not the AXI one, and you can go to the native ports and you can tell me, well, let's do a standard FIFO or a first word fall through. You can do first word fall through in here, and it will basically just implement that for you. And as you might recall, a standard FIFO can be constructed from a first word fall through by just attaching a flip-flop ahead of it. But you don't have to do it. You can just check this and it will do it for you. And then you can tell me the write width. Basically, remember this can be asynchronous, so you can actually write. This one here is telling me I'm writing words of 18 bits, but let's assume that you want to write 8-bit. And you can tell me the width in here, or the depth, sorry, how many rows you need, and you can go up to this number, okay, for example. Or let's just make it, for the sake of simplicity, let's make it 1024. And now the read width in here, it's telling me that you have these options. They're usually associated with 8, so that you have some sort of synchronization or something like that. All right, and now if you have any error connection and you know anything about error connection, you play around with these. If you want to initialize it, for example, for a reset pin or whatnot, like you can deal with that. Status flag, these are important because FIFOs usually, you don't only read and write into a FIFO, you also want to know whether it's empty or not empty. So there's a couple of other optional flags that you can say, well, is it full or almost full? It's actually okay, and you can specify what almost full is somewhere in this, within this here. It will show you. I think you have to read the documentation to figure out what almost full means. Okay, and then we can go to data count, for example, if you do care to see how many data points are written and valid and so forth. Anyway, you can go in here and you can say, all right, here's a specification, here's everything we need. Okay, let me just double check. Yeah, I think everything is fine. And you can, I forgot to mention this one here. For example, this is the FIFO. This is the right portion of the FIFO. And if you click in here, it shows you all the signals. It shows you the D input and the write enable. It also shows you a flag that is full. So if your system is trying to write to a full FIFO buffer, this full will be asserted so that you know it's full. You shouldn't be writing into it. The same goes with the read. You usually have a D out and a read enable so that you can discard the first one at the head of the FIFO and just read the next one. And it also has an empty flag so that you stop reading garbage. All right, so now we're going to click OK, and then we're going to generate it in here. And now that it's done, you can actually take a look at this FIFO generator in here, and you can see that it actually used 48 lookup tables, 60 flip-flops, and half a VRAM. It takes some resources off from you, but it's actually really useful. Anyway, so you take a look at your design sources, and you can see that we have a FIFO generator. If you double click on it, it'll tell you that, oh, it's too big, you shouldn't be opening it, or it's like maybe it's like it will actually open the wizard if you double click on it. But if you actually try this arrow in here, it tells you, well, like really for large IP, this may slow down source hierarchy updates and whatnot. Usually you don't need to do this. What you need to do is you need to go to IP sources. Usually anything you generated with an IP integrator or the catalog or the IP catalog, you will see it in here. And really here is the FIFO generator, and the reason why it's called FIFO generator is because probably in here we called it FIFO generator when it's like I didn't change the name, but you can change it to name it whatever you want. Anyway, it's called FIFO Generator 0, and now this is within the IP sources. If you could double click in here, there's a lot of information. I target the VEO for the Verilog. Okay, you can double click on that, and it contains the instantiation template. So all you have to do is just take this particular code in here, okay, and you can read whatever it generated. But for example, I can copy this guy in here, and whatever code I have, wherever it is, I don't care whatever it is. For example, you can just do this, and I just threw a FIFO in that particular design. This is the clock. You can figure out what this S reset, for example, a D in, a write enable, a read enable, a D out, the empty, and the full.